All right, so when we left off last time, we were talking about sequences, and I had given you a couple of sequences, and we had figured out a formula, recursive and explicit formula for those sequences. But what if we do things in the other direction? So what if I give you a sequence formula that looks like this? So I've got a sub n equals n squared plus 1 over n. Sometimes you might also see it written this way, where it's just written as n squared plus 1 over n with the little curly brackets, and that is also a sequence. So first thing I might want to do is I might want to write out the first 5 terms of my sequence. So a sub 1 is going to be 1 squared plus 1, which is 2. 2 divided by 1 is 2. So let's just write that out like that. A sub 2, 2 squared plus 1 is 4. So I get 4 plus 1 over 2, which is 5 halves. All right. If I put in a 3 for n, 3 squared is 9. 9 plus 1 over 3 is going to be 10 thirds. And then if I do a sub 4, the fourth term is going to be 17 over 4. The fifth term then, 5 squared is 25. Add 1, I get 26. So if I start writing out the terms of my sequence, I'm going to get 2, 5 halves, 10 thirds, 17 fourths, 26 fifths. And this will keep going, right? I could keep moving on and on. What is that? Where is that going? Is that approaching a limit or is it not approaching a limit? So I've got 2, I got 2 and a half, I got 3 and a third, 4 and a fourth, 5 and a fifth. It seems like it just keeps going up and up, but how do I know if that's actually the case? So what I would like to do is I would like to take the limit of the nth term as n approaches infinity. Well, how do I do that? What is my formula? My formula is n squared plus 1 over n. I would like to apply the limit as n approaches infinity. Well, if I try any kind of direct substitution or anything, I'm just going to end up with infinity over infinity. So this seems like a good case to L'Hopital. Right? If I want to find the limit as n approaches infinity, the top and the bottom both go to infinity, so this is a case of infinity over infinity. That's certainly a case for L'Hopital. So let's try that. Take the derivative of the top, and the derivative of n squared plus 1 is 2n. The derivative of the bottom piece is just 1, so I get 2n. Anytime you L'Hopital it once, you L'Hopital it again. So if I now apply the limit as n approaches infinity, again, I get infinity. So this does not approach a constant. Right? It does not approach a finite limit, let's call it that. And so if that's the case, we saw this back when we did integrals in the last chapter. We can say this thing diverges. And by saying it diverges, what I mean is just that the values get larger and larger and larger and does not approach a specific limit. Okay? Let's take a look at another case and see if we can find sort of a contrast in there. Nope. How about this? So suppose I look at this sequence. My a sub n's equal negative 1/2 to the n. Let's start at n equals 1. Right? So a sub 1 will be negative 1/2 to the first power, which is just negative 1/2. A sub 2 will be negative 1/2 squared, which is positive quarter. A sub 3 will be negative 1/2 to the third. If I do that, I still get a negative 1 on the top, and 2 to the third is 8, so I end up with a negative 1/8. So this looks like the signs keep alternating back and forth. A sub 4 then will be a positive 1 over 16 and so forth. So I got negative half, positive quarter, negative eighth, positive 16th. All right, what's happening to this sequence? Right, if I start making myself a list, my sequence goes negative, it goes positive, it goes negative, it goes positive. Is it approaching some value? Well, maybe it'll be helpful if we make a little sketch. This is not going to be the world's most perfect sketch, but let's see if we can make a little sketch. So when I do this, I'm not going to connect the dots because these things are discrete. So on this axis goes my n's, on this axis goes my a sub n's. So there is no 1.5 term, so I wouldn't connect the dots when I get done creating this. All right, so the first term we said was negative 1/2. That looks like it's roughly down there. The next term then will be positive quarter, so that's up here. The next one then will be a negative eighth. The next term will be a positive 1/16th, and what you can see is that these terms are approaching zero, but they're not approaching zero from one side, they're approaching zero from both sides. Is that okay? Yeah, because by the definition, it doesn't have to approach on only one side. You can approach that limit from both sides as long as it approaches the limit in the end. So in that case, we say it converges. Right? So in this case, the limit as n approaches infinity of my a sub n's is 0. In general, we say this. If the limit as n approaches infinity of the a sub n's equals some value that is finite, right? That limit is some finite value. It's not infinity. It's finite. Then the sequence converges. Otherwise, it diverges. So if it approaches some finite limit, then a sub n converges. If it doesn't, then it diverges. So that sequence that we saw before, that thing diverges because it doesn't approach a limit. This one converges. So what if we take a look at another type of sequence? All right, let's take a look at this sequence over here. In this case, let's look at a sub n equals cosine of pi n over n. All right, it's a little different sequence than we had before. But yet it's moving. All right. So let's write out the first few terms of this sequence. I've got cosine pi over 1. I've got cosine of 2 pi over 2. If I'm looking for a sub 3, I got cosine of 3 pi over 3. I got cosine of 4 pi over 4. And I can keep going, right? Funny thing happens with these pi's. The cosine of pi is negative 1. So I get a negative 1 over 1, which is negative 1. Cosine of 2 pi goes back to the cosine of 0, which is 1. So I get a half. Cosine of 3 pi is going to be the same thing as the cosine of pi. So that'll give me a negative 1 on the top and a 3 on the bottom. This will give me a positive 1 on the top and the 4 on the bottom. So it looks like what I'm actually creating is a sequence that alternates back and forth. Let's write out some terms. I've got negative 1, then I've got positive 1/2, I got negative 1/3, I got positive 1/4, I've got negative 1/5. You notice that as these numbers on the bottom get bigger, I begin to approach 0. But again, just like the last one, I begin to approach it from both sides. So this thing here converges, and the limit as n approaches infinity of the a sub n's is 0. Okay, so this one looked a little weird at the beginning, but once you start putting in those values, then you start to see where this is heading. All right, let's take a look at another one. Okay, in this case, I will look at a sub n equals 2n cubed over 4n to the 5th plus 2n. Sometimes you'll see this also written in bracket notation with something like this, n equals 1 on the bottom and infinity on the top, just to tell us that the sequence starts at n equals 1 and it keeps going. It's not a finite sequence, it's an infinite sequence. All right, so what if I decided to write out the first few terms? I could set myself up with a table and let the calculator run through this, and I'll come up with a third, right? That's the easy one. I could do that one in my head. And then the next one, I threw that in my calculator, and I got 0.121. I got 0.055. I got 0.036, and it kept going. So it looks like it's heading down towards 0, but How do I know that it's actually going towards 0? How do I know it's not going towards like 1/12 or something like that? Well, again, this seems like another case where if I take the limit as n goes to infinity, I'm going to end up with a case of infinity over infinity. So I could L'Hopital this a couple of times, right? I could L'Hopital 3 times. That's a possibility. Or if you go back to what we did in Calc 1, you could divide the top and bottom by the highest power, right? You could divide the top and bottom by n cubed, right? That's the highest power on the top. Or, so how about I divide numerator and denominator by n cubed? And that gives me the limit as n approaches infinity of a 2 on the top. I got a 4n squared over here. If I divide that by n cubed, I end up with a 2 over n squared. But really, this thing will begin to approach 0. And so if I apply that limit, I really do get 0. So this thing also converges. All right, let's take a look at another case. All right, so we'll move this up, and we'll look at this sequence over here. A sub n equals negative 2 to the n power. All right, so my first term is going to be negative 2 to the first. My second term will be negative 2 to the second. My third term will be negative 2 to the third, which is negative 8. My fourth term will be positive 16. And because it's an infinite sequence, it just keeps going. Where's it going? It's going below the axis, above the axis, but every time I do it, it's getting further away, right? It's down here, then it's up there, then it's way down here, then it's way up there. And so that thing is not approaching a limit. If you look at just the top half and just the bottom half, it's going in completely separate directions. So this thing diverges, does not approach a limit, right? Just keeps getting bigger and bigger. It keeps going back and forth between being very positive and very negative, but at the same time is not approaching some limit. All right, let's take a look at one more problem from here. And this one, I'm going to try typing out because it's easier than me writing this whole thing. So suppose I've got a ball is thrown up in the air, hits 15 feet, comes down, and it bounces to 75% of its previous height. What is the height after the 10th bounce? All right, so we'll put this up here. All right, so I got a ball that's thrown up in the air. It hits 15 feet, and then it bounces back to 75% of its previous height. So on the first bounce, it sort of looks like this, right? It's thrown up in the air, hits 15 feet, and then it comes back down. That's the first bounce, right? That's the first time that it hits the ground. And then the next time it's only going to go up to 75% of its height. Then it's going to come down. So by the time it hits the 10th bounce, my question is, how high was it? So at that middle point here, so it was 15. And then here it was 15 times 0.75, right? And then it'll be 15 times 0.75 squared. So it looks like, at least the way that I numbered this, that exponent there is going to be 1 less than that term there. So if I carry this all the way down, by the time I get to my 10th bounce, I should be at 15 times 0.75 to the 9th. And then you can throw that in there to figure out what 15 times 0.75 to the 9th is. It's not going to be very tall. Here, let's throw this in. 15 times 0.75 to the 9 gives me 1.126 feet. So before it hits that 10th bounce, that's how high it will be up in the air. All right, we'll do a little bit more with sequences, but we'll do it in part 3. So hang on, another round is coming.